Thank you very much, Gary, for those kind words, and thank you to everybody for taking the time to be present here. I think the best way to start this is to, as a student of hydrology, to look at the water cycle, which describes how we actually get the water we see on the surface. And so this is the hydrological cycle. But the most important thing to look at here is that the water which we have is the difference between the water that falls as rainfall and the water that goes back into the atmosphere as evaporation or evapotranspiration. Now, what we are seeing now is that the climate is affecting these two components. And once these two components are affected, then effectively, the net result is an impact on the water security which we have. So this is what people say is the greenhouse effect. This is what farmers use to grow crops in greenhouses. And what you see here is that the roof of this greenhouse allows the sun radiation to come in. But once it comes in, when it's going back into the atmosphere, it's not able to go back because of this roof. And so the greenhouse gases which we emit as part of our activities on the Earth's surface are behaving exactly like this roof. And so what you have is that as we pump more and more of these greenhouse gases, carbon dioxide, methane, water vapor into the atmosphere, the ability of this heat to escape our Earth's surface reduces. And what you have is this rise in temperature. So that is the whole problem. That's why we say you must reduce these greenhouse gases, because the more of them you have, the larger quantities you have, the larger concentrations you have, the more this temperature actually rises. So this is a chart of the global temperatures, and here we can see three epochs. The first pre-industrial stage where people were using proxies to actually get the temperatures, and then we have periods where we have observational facilities to actually measure the temperature. And then we have this epoch of the future in which we have to project, because we don't know what the future holds. So what we can do is to project. And this projection takes place using large computer programs, which we call GCMs. And what you see here are mean projections of the temperature until 2100. You see this rise in temperature. Now, these are mean values of these temperatures. And these bars here actually show the range of possibilities. So you have these GCMs, very complex programs, but they're not even agreeing amongst themselves of what the future temperature is. So if we don't know what the future temperature is, then we don't know what the impact will be on our climate, if you like. So you have this problem of how do we know exactly what the future holds? Because these GCMs, despite all the advances in scientific knowledge, have not been able to agree on what the actual amount of temperature changes will be. So this is what we have. We have this thing changing. We are already experiencing increased temperatures. We are experiencing stormy events in terms of rainfall. We experience more droughts in various parts of the world. And this climate change is having effects on virtually every aspect of our life. And unless we do something about it, the problem is just going to get worse. Let's hear what Jeff says about this. So that is what we're having to contend with, the fact that the climate is changing. And expert opinion actually says that this change is due to activities of humankind. So it's the activities we do that are causing that. And these are causing changes in rainfall, temperature, evaporation, as I've said. And what happens with that is that once these are affected, the water security is also affected. Now, we have to quantify these impacts so that we can make proper adaptation arrangements to make sure that we continue to get the water for the various activities which we need. Now, the way people have gone about this impact assessment is to sort of come out with mean impacts. What is the mean impact? But what happens in practice is that these mean impacts do not tell the true story, because there is a large variability in the possibility of impacts. And to be able to make meaningful decisions, we have to actually characterize not just these mean impacts, but the multitude of possibilities, so that decision makers have full information about how we are going to adapt or mitigate these climate change impacts. So these are the ways in which these uncertainties arise. Now, I've told you before that we don't know what the future is, so we got to project. And these projections are carried out using what we call global climate models. Now, these models have a series of steps in them. And this series of steps, at every stage, we are introducing uncertainty into the problem. Now, at the end of the day, even when you don't have these uncertainties, when you now start looking at the impacts, you are looking at a single scenario of the impact, whereas what you should be looking at is the various possibilities of the future. The future is not a single scenario. The future, because of what we call the stochastic, the random nature of the process of rainfall, the future is not just a single realization. There are various possible realizations. And we need to capture all that to be able to make meaningful statements about the impacts of climate change. So I'm going to illustrate this with two examples. The first one was the one we did for Yorkshire water in England after the 1995 drought, which saw large areas of Yorkshire running out of water. And then another one in India, which we've recently completed in the Himalayas. These are two different scenarios. This one has a characteristic of a catchment being in an area where you have a lot of glacier and ice, and the characteristics and the challenges that poses will be looked at in this particular discussion. Now, this is what drove the Yorkshire study. There was a lot of drought in 1995, and this was predicted to increase. Now, there was a lot of pressure on water resources, and despite all manner of conservation, saving water, preventing people from using water for watering their gardens and all the rest of it, the problem did not go away. And people attributed that to climate change. Now, one possibility is to develop new sources. That takes time. To get a reservoir developed in this country can take up to 30 years to do. So it's not something which you can just arrive at. So they really wanted to look at what the problem is, how much water do they have, and what should they be doing in terms of meeting any shortfall. So we're called upon to look at this problem. These are some of those reservoirs which literally ran dry in 1995. A lot of them, and we want to look at how we can, first of all, tell Yorkshire water what climate change holds for these reservoirs, and whether or not they will have sufficient water to meet their demands into the future. Now, these are real systems. These are not hypothetical systems. You have large cities in Yorkshire that depend on these reservoirs for their water supply. So not being able to meet the demand for this in a sophisticated society like the UK is going to carry a lot of headline news. So we now say, okay, let's look at the impact of climate change. And what we have here are what we call scenarios. Scenarios are projections of what we hope will happen in future. And as I told you before, these are done by global climate models. And there are a large number of such global climate models. The UK has its own. All the large countries of the world are competing with themselves to develop these GCMs. And applying these GCMs to the same location will give you completely different outlook for what the future is. Now, the problem arises, which one of them do you believe in? Now, this is a climate model developed by the Canadians for the Yorkshire area. And these are different time horizons into the future, up to the 2080s. And what we are seeing here, that for that area, there will be wetter winter, and the bulk of the rest of the country will actually be drier. Okay? Now, if you have dry periods, then the water available will obviously shrink. This is one GCM. This is Canadian. The Canadian will say, their GCM is the best. Now, let's look at it. This is something by the Australians. This is Australian GCM for the same catchment. Now, it's saying that throughout the whole period, we should be experiencing a higher amount of rainfall. Now, that is good news, because higher rainfall means higher water availability and less stress on available water resources. Now, closer to home, this is the Hadley Centre, the UK GCM, the same area. Now, the Hadley Centre GCM seems to sort of agree slightly with the Canadian, but totally at odds with the Australians. And it's also saying that you have significant reductions in precipitation during the winter months, during the summer months, and some higher amount of rainfall during the winter months. This is one of the problems that we face in the impact communities, because these scenarios are never converging. They are never given the same thing, even for the same particular catchment. And the fact of the problem is, which one of these do you actually believe in? So that is the rainfall. In terms of the evaporation, that is water going back into the atmosphere. Remember, I told you before that the total amount of water available is the difference between the rainfall and the evaporation. So we've got to look at two climatic factors. Now here, in the Canadian, we say evaporation is likely to increase overall. In the Australian one, it's a mixed bag. It's not consistent. Of course, the UK one saying is that because the summers are drier, evaporation potential is also much higher. So you begin to see here that the UK model is projecting the future to be much, much drier, because both the rainfall is reducing and evaporation is going up, which means the net water available will be much smaller. Now, this is all these things. So you put them into a model. Nobody is interested in evaporation or rainfall. What people want to see is how much water is available. So put this into to drive a hydrological model, and this is what we have in terms of the water coming in. Again, you expect the Canadian one to say there's less water in this area, because that's why you had less rainfall. The Australian one is what we expect, because it's saying, a lot of rainfall throughout the whole period, so you have more water. And of course, the UK one is saying this is what you have. Okay? So which one do you believe? And you are, as experts in the impact community, you are meant to give advice to policymakers, to people in Yorkshire, for example, to see how they manage their water resources. But we sat down with these managers at Yorkshire Water, and we told them, what exactly do you want? They said they are not interested in the runoff. They want to see the ability of their systems, the reservoirs, to be able to continue to meet the demand into the future. So yes, we got them the runoff, but they really want to see what impact that will have on their reservoirs. Are these reservoirs able to give the amount of water they need or not? So that's the important bit there. So it means we haven't got to the end point. We need to do more simulations to be able to carry and give them more information about how much those reservoirs will be able to provide in the future. So this is what we have. We have a complex network of reservoirs. I don't want to bore you with that, but this is the way we schematized it and used a simulation, a well-behaved simulation approach which we developed here. But we didn't just give them what the main impact of these climatic changes on the amount of water the reservoir can supply. We also gave them the various possibilities, the uncertainty range. So this is what we have. This is the Canadian one. If you look at the main impact, how much we are going to have in the future. Now, this is saying that in the 2020s, for example, the yield which these reservoirs will be able to supply will be less by this amount, increased by this amount, increased by that amount, on average. But the reality is, the possibility is very large. The amount of yield that can be supplied can decrease by as much as 12% and can increase by as much as 10%. Okay? So people would be wiser if they have this sort of information, which gives them the various possibilities, rather than saying, I mean, it would be disingenuous for me to say that in the 2020s, the yield will just fall by 1.8%, because the likelihood is that the yield might actually fall by 12%. So this is the Canadian one. Now, this is the Australian one. Australian one is saying, yeah, because we're going to be wetter in the future, the likelihood is that we will have increased amount of water available from this system. So you see here, this is the zero line. For the Australian one, is all increases in the future, which is fantastic if it turns out to be like that. The problem is you and I don't know whether it will turn out to be that way. Now this is the UK, sorry. This is the Hadley Centre UK one. And again here, these are the main impacts. Consistent reduction in the amount of water from this reservoir in the future, but the variability is equally high. So these are some of the issues which we encounter in the impacts community. How do we sort of use these sort of high variability results to inform decision making? It's a major issue. But I think decision makers will be much more satisfied if you let them know that what you are contending with is highly variable, that there's a lot of variation in it. And so they can decide what the best action is to actually take to mitigate this impact. So this is a summary of what we have, which is more or less similar to what I had before, in the sense that you had these main impacts. This is the Canadian one, this is the Australian one, and this is the Hadley Centre. These are the main impacts, but here you have the large variations in this particular impact. So it's not correct to tell people and that this is what is going to happen in the future. Yes, you tell them this is what is going to happen in the future, but there are various variations in what is the likely impact in the future. So this is what we ended up with the Yorkshire one. And since they got this result a few years ago, they've tried to implement some of the decisions we arrived at. And the good news is, over the years, even though droughts have occurred, but the sort of negative headline we got during the 1995 drought, we haven't got it again, because they now know that the impact of climate change is highly variable, and they have to be ready to cope with these large variations in impact. The other one is the Indian study, which we carried out in India recently. And this was part of the agreement between the UK government and India to sign an agreement to try and look at ways by which Indian and UK scientists can collaborate in the area of climate change, the changing water cycle, so that the expertise of India and the expertise of UK could be brought together to solve this, what is essentially a global problem. So this thing was part of the Changing Water Cycle South Asia program. The UK part is being funded by Research Councils UK, and the Indian part is being funded by the Indian Ministry of Earth Sciences. Now, it's a much larger project which involves various aspects, not just water, areas of agriculture and all the rest of it. And it involves a number of institutions in the UK and in India. But I'm just going to talk about the water resources study there, so that you can get a feel for these uncertainty issues which I mentioned before. So this is the basin we looked at. It's in northwest India. It's located in the part of the catchment has a lot of snow and glacier. This is located in the Himalaya, which we all know as Mount Everest here. It's a very nice place to visit. If you go to India, you see all the snow. Now, this catchment has about 8.9% of it covered in snow throughout the whole year, and temperatures are extremely low. Now, the water there is used for various purposes. We were asked to look at this reservoir, which is a reservoir which has been established to provide irrigation water and hydropower, because people are beginning to notice that the hydropower yield of this reservoir was declining, and also irrigation water deficits were occurring on a regular basis. So we needed to find out what climate change is saying, and we need to develop for them better ways by which they can operate this reservoir so that some of these problems can be mitigated, if you like. So this is just to show you before we go into this is the Grinnell Glacier in Montana in the USA, and this is the picture in 1938, and this is the picture now, and you see all this glacier is now melting and becoming runoff. Okay, now I took a picture of the Himalayas when we were there, but inside my system I couldn't see it. But then what I'm trying to show here is that this climate change is not just affecting rainfall and evaporation, it's also affecting the quantity of this glacier. Now, the Himalaya is different from this. The Himalaya has the nickname of the third pole. So after the North and South Pole, the next area where you have a large abundance of ice sheets is the Himalaya. And so the melting of that is going to have profound effect on the ability of people in this area to actually sustain their water resources needs. So this is what we have for this system. What I want people to look at here is the irrigation water demand. This is the amount of water they require for irrigation. And this one here represents the flow in the river. The flow in India is highly seasonal. A lot of flow during the monsoon period when most of the rainfall falls, and in other periods the amount of rainfall is very low and whose the river flow is very low. Now, I tell my students that there's no way you can meet this demand in this area from this river unless you have a dam, because the amount of water required is more than the flow in the river. So the pond reservoir, which we are looking at, has been serving a very useful purpose over the years to be able to provide the amount of water needed for irrigation. So this irrigation and in all these areas of India rely on this reservoir for hydropower generation and for irrigating the farms of farmers. So what they are interested in, as far as climate change is concerned, is this reservoir able to continue to meet the demand in the future? Yeah. If it is not, what is going to be able to happen to the ability to meet those demands? How are you going to be able to do it? And secondly, they want to know whether the performance of this reservoir will continue to be acceptable in the future. And so these are the things which we investigated. Will it be able to meet the acceptable level of performance in the future? And will the existing size be sufficient with climate change? And if these two are incorrect, how do you solve the problem? And what we are saying is, how do we better operate this reservoir to be able to accommodate this problem? So this is a climate change issue, similar to what we did in the Yorkshire, and we applied the same approach. Now, somebody was asking me, do I have equations? These are not complex equations. These are very simple equations which tell us the performance indicators of reservoirs. I don't think the professor of engineering can give something without having one or two equations. They're not terribly important. But this gives us the ability of that reservoir to meet the demand, and this gives us the sustainability, and this one gives us the vulnerability. I just want you to have this at the back of your mind, that the ability of the reservoir to meet the demand can actually be quantified. And the two important things which I'm interested in is what proportion of time the reservoir is able to perform satisfactorily, and what is the maximum shortage possible from this reservoir. Now, one of the problems of doing research in India is that getting data can be extremely difficult. Usually, when it comes to water, Some of the rivers are taken as sacred, and so they rarely share the data with international people. So you got to go through a lot of back deals, backhand deals, to be able to get this data. So people wanting to do research in India have to bear that in mind. Now they have a reservoir which they are using for generating hydropower and for irrigation. And we told them that you must be operating this reservoir using some operating rules. How do you release the water from the reservoir? And they said, no, they don't. They use rule of the thumb. So we said, that was not right. So we now developed a policy for them with which they can operate this reservoir. Without going into too much detail, this is a tool which enables you to release water from the reservoir. So if you have your water in this area, then you can continue to meet your demand and so on and so forth. So we developed this tool for them using what we call genetic algorithm. It's a very simple tool which mimics survival of the fittest. So we developed that, and it's now being used in Himachal Pradesh, for example, to operate this reservoir, and they have begun to notice significant improvement in the performance of this reservoir. We'll come to this later on, because this is just a basic tool. We have refined it to make sure that the performance of the reservoirs has significantly improved. Now, this is the menace for the climate change. Now, I told you before, when I was talking about the Yorkshire, that we had 3 models. And those 3 models are the best suggested at the time of the investigation. Now, things have moved on since then. A lot of scientific developments have taken place. And rather than using the approach in those periods, they are now using a different approach. I mean, this thing here are what we call the amount of additional radiation. I showed you the greenhouse model in which the radiation is not able to escape and is causing a rise in temperature. And so the approach now is to try and look at different such radiations and see the impact they have on the climate. So they have this what we call representative concentration pathways. This is the this is the coupled model intercomparison project undertaken by IPCC. IPCC is the world body looking at climate change and how it affects us globally. So they have all these models. I talked about 3 previously. Now here we had a total of 127 GCMs running different things and providing different possibilities. These are different combinations of rainfall and temperature in these time slices. Now this is a problem. Now the climatologists will give us this information. Those of us in the impacts community have to make sense of this. Okay? How do you analyze this? I mean, if you take 127 different combinations, it means you're going to get 127 different projections of what is happening to the water in the future. We don't want to do that. So what we did was we looked at this system here. If you look at these crosses here, these crosses are the centroid of these chaotic projections of temperature and rainfall. So we took those things and we sort of tried to make sense from it and say, all right, supposing we look at those crosses and then find the mean and the standard deviation of the observations, then we could construct, 95% confidence of the likely variations in temperature and likely variation in precipitation. Okay? So rather than me running 127 simulations for that catchment, I can come up with very simple perturbations in temperature. So based on this sort of thing, I came up with these tested perturbations in temperature and tested perturbations in precipitation. Okay? And make judgment on the basis of that. Okay? And what we are doing here is to try and present possibilities in the future, rather than being stuck with this 127 possibilities. So this is another issue I'm talking about the problem associated with climatic change in terms of, the GCMs don't even agree, despite all the efforts that have gone into further understanding of the processes. So this is the dam. Of course, we see this is evaporation, this is rainfall, this is the runoff coming in. These two are affected by climate change. If these two are affected by climate change, what comes in is affected. Now, something which we have not considered is the demand. People even believe that people should stop talking about climate change I should start talking about how you reduce the world population, because the impact of that could even be more profound than changes in temperature and evaporation. So, but we have not even touched this at all. We're just looking at the climatic elements there. So this is what we have. If you bring all this together and put it in that catchment, this is what you have. These are changes in rainfall. You know, I said we're looking from -10 to 20%, and these are changes in temperature. And what you see here, effectively, is that increasing the rainfall will naturally increase the runoff. That's what we expect. More rain, more water. You know, you get flooding when you have water. If you don't have water, you have drought. Okay? So increasing the rainfall causes this to change, to increase, and reducing it. But one thing that is peculiar to this basin is the fact that if you increase the temperature, remember, temperature increase will increase evaporation. Evaporation is water lost into the atmosphere. So if we increase the temperature, intuitively we expect the runoff to reduce. Yeah, because there's less water going back into the atmosphere. But here, we are not. Look at this 0 point here, which this is no change in rainfall, and we are increasing temperature. What you have here is that we are actually increasing the runoff. And the reason for that, for this particular, if I run this in the UK, I'm not going to get this result. I will get a completely opposite result. But because of the glacier melting and the snow melting in that part of the world, the increased temperature is causing the glacier to melt. And the melted water is overcompensating for any increase in evaporation caused by a temperature rise. And so you have this, I wouldn't call it an anomalous behavior. It's a behavior which we expect for this type of catchment. But it's a behavior we wouldn't get if I was looking at a catchment in my native Nigeria, for example, or another country that does not have this glacier and this snow melt. So what we have here is that increasing the rain will increase water, reducing the rain will reduce that, and this is what we have here. But as in the case of the Yorkshire one, the people are not interested in whether I have more runoff or not. They want to see what is happening to the performance of their reservoirs. But before we go into that, this is just the annual pattern. We also have the seasonal one. Remember I said that, you know, the Himalaya or India has a very seasonal climate in terms of the rainfall. Most of the rain comes during the monsoon period, and that's when you have most of the runoff. So the pattern is more or less the same. There's no major difference there. So what I'm saying here is that the people are not really keen on that. The water resource manager wants to know what is the likelihood of his reservoir being able to generate the hydropower, or how much hydropower can it generate, or how much water can be supplied to for irrigation to the farmer. So they're not interested in some of this. This is very important. This is an intermediate stage of what we do as impact modelers in the impact community. So this is without boring you with the details of what went on. We said, you know, what happens if climate change causes the water to decrease? What happens if climate change causes water to reduce? This is the result of a lot of simulations. You know, we carry out a lot of water resource simulations to be able to do that. Now, I showed you previously the equations which relate to the performance indicators of the reservoir. This is the ability of that reservoir to keep on meeting the demand. And this is a measure of how vulnerable the system is to water shortage. Vulnerability, we define it as the maximum single period water shortage. So if it is a large water shortage in a single period, that is going to cause a lot of mayhem for people who rely on their water. Whereas if you have small reductions, people are able to adapt to that and move on with their lives. Okay? So if you look at this one here, if you have anything causing flow to increase, the proportion of time in which you meet the demand will go up, and the amount of water you supply will go up. The shortage will go down. That's what we expect. This is common sense. Now, if the climate change is reducing the inflow, the opposite will happen. But when we carry out these so-called mean simulations, the mean, I'm not still talking about the variability. I'm talking about the mean impacts now. When we carry out this mean impact, we find out that even when these things do deteriorate, they are still acceptable. Now, if my students scores 88% in my exam, I would say, you've done extremely well. I wouldn't frown at that. Very rarely do they score 88 in my exams anyway. So, but it's something which you will be proud of as a teacher. Now, the problem we have here is with this one here, where the amount of water shortage becomes very high. Now, generally, in most developed parts of the world, including the UK, by the time you have more than 25% water shortage, people will start making noises. People will start crying. Okay? So 0.25 fraction is seen as, a threshold which you do not want to cross as far as water shortage is concerned. Now, but we found out that with this mean impact, that the shortage is still 50%. Now, in some parts of the world, 50% demand supply is good, but here it's not good. In developed countries, it's not very good. So once it exceeds that level, then you start having problems. So it means that this thing here, yes, the climate change, as far as the proportion of time is concerned, is okay, but in terms of the, period of water shortage, it's not very good. So we have to find a way by which we actually solve this problem for them. This is what they want us to solve. They want us to solve this problem of single period water shortage that are very excessive. And the way to do that is to operate that reservoir in a way different from what I said previously. So this is what we have. The way to do that is to hedge water. Now we know in the UK when a new government comes in, the chancellor will say, the previous government didn't save for the raining day, and that is why they're having problems. And then the other one will come and say the same thing. Now, what we are saying here is not just the economy that has to save for the raining day. Water also has to save for the raining day. And the impact of this is that a very little saving for the raining day will avert much bigger shortfall in the future. So we call that hedging, save. You have water, you have enough water, but you will not release it. You keep it aside so that you can use it towards, next period when things are going to be extremely dire. So you now have something to go towards that. Now, hedging is not something which you do lightly. It's a very complicated process. Just like the chancellor will know, it's very complicated. So we have to find a way by which we develop a policy which will enable the hedging to take place. Now, without going into too much detail, we also used our genetic algorithm. I have people here who are, hotheads in genetic algorithm. So they developed this. And what we have here is, previously, you see, we had everything here possible for supply. But now we developed a third curve here, which is what we call the critical curve. And what we are saying is that once we fall below this line, we start hedging, okay? So the development of this line is not straightforward. It's based on, a lot of optimization with genetic algorithms. And this one here is the hedging fraction, i.e., rather than supply the full amount, we are supplying 83% of the amount, which is we are reducing the amount they need by just 17%. Now, that is very good because it's still below my so-called critical 25%. But as you will see later on, it had a significant impact on the overall vulnerability. So this is what we have. Let's look at this. Let's forget about these two columns. Okay? Let's look at this column here. Okay? I said I wasn't happy with the vulnerability because I was having too much shortfall in some single periods. I don't like it. And this is what you have. This H0 is when you just live as usual. You use your water anyhow. assuming that you always have water. Now this one is when you hedge, you put some water aside. And you see here all the vulnerability for different climate change scenarios. This is 1 degree centigrade rise, this is 2 degrees centigrade, this is no rise. All the vulnerabilities are way, way above my 25% threshold, which I said, people can adapt to. I mean, if your water shortage is 25%, you should be able to adapt to it. Most of the water in the homes, you waste them anyway. You turn the tap and brush your teeth for several hours. So that's a waste of water. Now, if you now do the what I told you about in terms of hedging, you see what we have. This thing has dropped significantly from almost 65% to less than 25%. Okay, so water hedging helps us to reduce this single period water shortage. Now the good thing is that the people at the BS Bakra Management Board are now using this to operate the reservoirs, and they're reasonably extremely happy with the outcome they are getting in terms of the effect on the performance of the reservoir. So this is all about mean impacts. I'm not interested in mean impacts. I really want to know what the overall possibilities are in terms of this thing. So this is the final thing in terms of the hedging. It helps a lot in solving some of these problems. But the problem here is not just about the mean impacts. The problem here is what is the variability, what is the likelihood? And here you have the required reservoir storage. Now this line here is the existing reservoir capacity in our reservoir. These are possibilities of temperature and rainfall scenarios in the future, which we had before. We had 0 to 5 degrees centigrade increase and different changes in precipitation. And what you see here is that when the system is very dry in the future, the reservoir you require will be much higher than what you have now. You cannot sustain that system with what you have now. But when you are in the future and you are wet, then, well, the reservoir is what they call white elephant. It's much bigger than surplus to what you need. But it's good. That's a good safety factor. But we don't know where we are going to be. We could be here, we could be there. One other thing which I want you to realize here is the large variability when you have dry conditions. See, the reservoir requirement can vary from here to here. Large variation. Which one do you believe? Now, a good thing for some of my colleagues who are working on flooding, because flooding is excess water, is that the variability in those areas, although we are talking of different temporal scales here, the temporal scale of water resources is different from the temporal scale of flooding. But what I can deduce from this is that flooding variability, as far as climate change is concerned, is much, much less than the one you get during droughts. Okay? Now, for people who are interested in conventional CDF, this is what you also have. It's the same thing. What I'm just trying to say is that if the catchment is dry, then the variability is extremely high. If the catchment is wet, the variability becomes extremely much reduced. So this is the same information which I've plotted in the other one, but this case using a different approach. This is what we call the coefficient of variation. This is a measure of the variability. And again, we can see that. But one thing I like here is the variability of the reliabilities. This is what we use a lot in water resources. We use what we call return period. So people say the return period of a flood event is 100 years, but the probability that it will be exceeded is 0.01. Now that's a measure of the reliability of the risk. We use that. But I found out here that those indices are very, very robust. The variability of these indices is very, very low. If you look at all these things here, they're the least variable there. And that, to me, sort of gives credence or gives acceptability to the use of return period for characterizing risk in water resources. So this is the summary of that in terms of the Indian one. Capacity, we've told them, the capacity which you have now may not be sufficient in the future, or it may be excessive. It depends on what the future holds. But we can attach probabilities to them, and that's what we've done with that. Performance indices also highly variable, but the reliability is the least variable. That's what I'm saying. But our continued use of return period to describe droughts and floods should continue, because the variability associated with those indices is usually very, very low. So these are I'm running out of time. These are my final thoughts on this climate change. I've taken you through two examples. There are a lot of other examples which we have done. But this is with us. And there's nothing we can do. We have to accept that it is with us. And it's likely due to our activities. It's not something that is imported. And so if it affects water, then by extension, it affects food security. It affects energy, health, livelihoods, everything, name it, anything you do. Water is so essential for this. And so our ability to continue to survive might actually be threatened as a result of this problem. Now, there are giant strides that have been made in the scientific endeavor, as we saw before. A lot of people are working, the IPCC is working every 7 years. They come up with their assessment report, which gives the state of art of knowledge in the subject. So it's continuing. I mean, there have been significant improvements from the Yorkshire study to the Indian study, significant improvements, but a lot still remains. And we need to sort of solve these uncertainties if we don't want to continue to fuel the skeptics' disapproval of this process. Now, lasting solution is beyond the realms of scientific endeavors alone. I think we need strong political will and leadership, and this is why some of us get agitated when world leaders are shying away from adopting some of these protocols to help cut these greenhouse gases. And this brings me to the Kyoto horse trading, the notion that you can buy the carbon rights of other countries and continue to live the way you want to live is not the solution to the problem. We need proper deals where everybody has to sit together and come up with, workable solution to the climate change problem. Because if we do not do that, then our good ways of life is not just Father Christmas that will be dreaming of White Christmas. We will always be dreaming about White Christmas because we will never get it. In as long as these problems actually persist. Now, I think I would like to thank a number of people. I've been fortunate in my career to have worked with exceptional people who have helped me along the way. And I'm indeed very grateful to all of you, students. We are all students. We are all learning. Colleagues, everything, my family, everybody's here. My wife is there. They've been supportive all the way. It's quite good. But above all, I thank my good God, because everything that has happened to me is serendipity. I don't know, it just happens. And for that, I think there's a divine power behind that. And I want to acknowledge that in this forum. I will leave you with this picture, this jamboree we had in India at the end of this Mickey project. These are scientists, but there you also have farmers. You have people, ministry officials, stakeholders engagement. Water resources is not something which I just sit down on my computer and do. You have to get, everybody involved. And so this thing is there. The website is there. We have some papers outside, some off-prints by the generosity of RCUK and Reservoir University. All those papers are open access. So if you want electronic copies, just send me an email. Thank you very much.